Welcome to the AWS Certified Cloud Practitioner Prepcast, where we guide you through everything you need to know for your certification exam. Whether you're just starting or looking to refine your knowledge, this course will set you up for success. Brought to you by baremetalcyber.com. Let's get started. When you launch an application in AWS, one of the most important choices you'll make is which EC2 instance family to use. Instance families are like categories of hardware profiles, each tailored to specific workload patterns. AWS provides families that emphasize balanced performance, raw compute power, large memory capacity, or specialized storage throughput. The goal is not to memorize every detail of every instance, but to understand the map of families and how they align to different needs. Beginners should think of EC2 families as vehicle types: sedans for balanced use, sports cars for raw speed, buses for carrying lots of passengers, and trucks for hauling heavy loads. Each is designed with trade-offs, and selecting the right one ensures your workloads are efficient, cost-effective, and reliable. General-purpose instances are the most common because they provide balanced ratios of virtual CPUs and memory. Examples include the M family and the newer T family. These instances are versatile, serving a broad range of workloads from web servers to development environments. They don't excel in any one dimension, but they provide good value for applications that need moderate performance across the board. For learners, imagine a general-purpose family car. It may not be the fastest or have the largest trunk, but it serves well for commuting, shopping, and family outings. In AWS, general-purpose instances provide that same all-around balance. Within general purpose, the T family introduces a burstable performance model. T instances operate on a baseline level of CPU, but accumulate credits when idle. These credits can then be used to burst above the baseline temporarily. This model is cost-efficient for workloads with intermittent spikes, such as small web servers or development tools. Beginners should picture a rechargeable battery. When lightly used, it charges up, and when demand surges, it has extra power available. The key lesson is that T instances are ideal when average usage is modest, but occasional bursts are expected. They save costs without over-provisioning. For raw processing needs, compute-optimized instances are the right choice. The C family delivers high vCPUs per dollar, making them excellent for batch processing, scientific modeling, or high-performance compute tasks. These instances prioritize CPU over memory, ensuring maximum throughput for code execution. Beginners should think of compute optimized as sports cars, built for speed and acceleration, but with smaller trunks. They're not meant for storing large datasets in memory, but they shine when executing millions of instructions per second. Workloads that are CPU-bound rather than memory-bound benefit most from compute-optimized families. Memory-optimized instances, represented by the R and X families, focus on providing very large amounts of RAM relative to CPU. These are built for workloads like in-memory databases, caching systems, and analytics engines that must keep large datasets in memory for performance. Beginners should imagine buses designed to carry many passengers comfortably. Memory-optimized instances are like buses for data, capable of holding far more in memory at once, enabling rapid access without repeatedly fetching from disk. They are the go-to choice when memory capacity is the bottleneck. Storage-optimized instances bring fast, high-throughput local storage into focus. Families like I and D include NVMe SSD drives that deliver extremely high input/output operations per second, or IOPS. These are designed for applications such as data warehousing, log processing, or workloads requiring sustained high-speed access to local disk. Beginners should think of these as heavy-duty trucks, less concerned with speed or luxury, but engineered to carry and move large loads of data efficiently. A critical distinction is that this storage is ephemeral. If the instance is stopped, local data is lost, so it must be paired with replication or backups. Network performance is another factor across instance families. Some instance types advertise up to a certain gigabit per second rate, meaning bandwidth varies depending on load and instance size. Others offer fixed guarantees, especially in larger sizes. Beginners should picture this as the difference between a shared public road and a dedicated lane. Up to speeds fluctuate with traffic, while fixed rates ensure predictable performance. Understanding whether your workload needs steady throughput or can tolerate variability helps you choose the right networking tier. EBS optimization is another layer to consider. Many modern instances include dedicated throughput for elastic block store traffic, ensuring disk I/O doesn't compete with network bandwidth. Some instances provide baseline performance, while others allow provisioned throughput for demanding applications. Beginners should see this as a reserved lane for delivery trucks. No matter how busy the highway gets, these trucks always have their space. For workloads where EBS throughput is critical, selecting EBS-optimized instances prevents performance bottlenecks. Instance naming conventions in AWS may seem cryptic at first, but they follow a logical structure. The family letter indicates the purpose: M for general, C for compute, R for memory, I for storage. The number indicates the generation, with higher numbers representing newer hardware. The size, such as large or extra large, reflects the scale of resources allocated. Sometimes attributes are included, such as N for networking enhancements or D for local storage. Beginners should think of it like car model names. C6i.large is akin to Honda Civic 2024 Sport. Once you decode the pattern, the name itself reveals the intended use. Architecture choices are another factor. AWS supports both x86-64 processors from Intel and AMD and ARM-based Graviton processors designed by AWS. Graviton offers impressive price-to-performance ratios and energy efficiency. Beginners should see this as choosing between gasoline and hybrid engines. Both can power the vehicle, but the hybrid engine, Graviton, provides more mileage per dollar while reducing fuel use. The compatibility of your application stack determines which architecture you can use, but for many modern workloads, Graviton offers significant cost savings. Behind many modern instance families is the Nitro system. Nitro is AWS's lightweight hypervisor platform that offloads networking, storage, and security functions into dedicated hardware. This maximizes the performance available to the instance itself. Beginners should imagine a house where utilities like plumbing and electricity are routed through separate conduits, leaving the rooms entirely available for living space. Nitro improves both security and efficiency, making instance performance closer to bare metal. Its architecture also allows features like faster provisioning and better isolation. Enhanced networking, or ENA, provides high-performance, low-latency network interfaces for instances. With ENA drivers, instances can achieve higher packets per second and lower jitter, making them suitable for high-throughput or latency-sensitive applications. Beginners should think of this as upgrading from a standard internet plan to a fiber optic connection. The difference in speed and responsiveness can be significant, especially at scale. Enhanced networking helps applications like financial trading systems or real-time analytics remain fast and reliable. Local NVMe devices are sometimes included in instance families, providing extremely fast ephemeral storage. Unlike EBS, which persists independently of the instance, local NVMe drives are tied to the life of the instance. If the instance stops, the data is lost. Beginners should think of this like RAM disks or temporary scratch pads, incredibly fast, but not for long-term storage. These drives are best for caching, temporary datasets, or high-speed processing pipelines where persistence is handled elsewhere. Placement groups provide additional performance and fault tolerance options. A cluster placement group groups instances close together for low latency, high bandwidth communication. Spread placement groups distribute instances across hardware to minimize correlated failures. Partition groups divide resources into logical segments for large-scale distributed systems. Beginners should think of placement groups as seating arrangements at a theater. Sometimes you want everyone together for collaboration, other times you want them apart for safety. Choosing the right placement strategy aligns infrastructure with workload priorities. GPU and accelerated computing families exist, but are outside the core families discussed here. These instances add specialized hardware for machine learning, graphics rendering, or scientific simulations. For now, it is enough to recognize that AWS offers dedicated accelerators, but general-purpose, compute, memory, and storage-optimized families cover the majority of typical workloads. Beginners should see GPUs as specialized vehicles like ambulances or fire trucks, not needed for every situation but indispensable when the job calls for them. The most important mindset when working with EC2 families is right-sizing. Rather than guessing, you should measure workloads with CloudWatch, test different instance types, and iterate. Over-provisioning wastes money, while under-provisioning risks performance problems. Beginners should think of this like tailoring a suit. It must be fitted to your body, not just chosen off the rack. AWS makes experimentation easy, and a cycle of measuring, testing, and adjusting leads to environments that are cost-efficient, resilient, and tailored to real workload needs. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. When it comes to mapping instance families to workloads, patterns quickly emerge. General-purpose instances are best for balanced applications like web servers and app servers, where neither CPU nor memory dominates. Memory-optimized families shine in in-memory databases such as Redis or SAP HANA, where large datasets must be held entirely in RAM. Compute-optimized instances are ideal for analytics pipelines or scientific simulations, where calculations, not storage, are the bottleneck. Storage-optimized types fit log processing and data warehousing, where large volumes of data must be read and written quickly. Beginners should picture this like assigning vehicles for tasks, a sedan for errands, a bus for passengers, a race car for speed, and a truck for hauling. Matching the workload to the right family is the essence of effective selection. Another key principle is the ratio of vCPU to memory. Each family has a characteristic profile. Compute-optimized instances offer many vCPUs relative to memory, while memory-optimized ones flip that balance. General-purpose families sit in the middle. Knowing whether your workload is CPU-bound, memory-bound, or balanced helps guide you. Beginners should imagine planning meals. Some recipes demand lots of ingredients but little cooking time, memory-heavy, while others involve hours of mixing and stirring but only a few items, compute-heavy. The right ratio ensures efficiency, preventing wasted resources on the wrong dimension. Burstable instances like the T family highlight the trade-off between baseline and sustained CPU. They work well when workloads occasionally spike above baseline but are inefficient for sustained, heavy compute demand. In those cases, M or C families are better choices. Beginners should think of burstable instances as a prepaid phone plan, perfect if you mostly stay within limits but occasionally need extra minutes. For constant, heavy usage, an unlimited plan like Compute Optimized makes more sense. This distinction often appears in exam questions, where the workload description hints at whether bursts or steady performance are required. Storage patterns matter as well. Some workloads thrive with EBS-only volumes where persistence and flexibility are crucial. Others, such as high-frequency trading or large-scale data analytics, benefit from local NVMe devices in storage-optimized families. Local NVMe provides unmatched speed but disappears when instances stop, so applications must handle persistence elsewhere. Beginners should see this as choosing between storing valuables in a safe deposit box, EBS, or keeping them in your desk drawer for quick access, NVMe. The drawer is faster, but only reliable if you have a backup plan. Understanding throughput versus IOPS helps avoid bottlenecks. Throughput measures how much data can flow over time, while IOPS measures how many operations can occur per second. Workloads like log ingestion demand high throughput, while transactional databases require high IOPS. Beginners should picture this as water flowing through pipes. Throughput is gallons per minute, while IOPS is the number of times you can turn the faucet on and off. Both matter, but the bottleneck depends on the workload. Exam questions often test whether you can identify which metric is limiting a scenario. As workloads grow, multiple elastic network interfaces, or ENIs, and higher bandwidth scaling become important. Larger instance sizes provide more network capacity, while multiple ENIs allow for segmented traffic patterns, such as separating management from application traffic. Beginners should imagine a busy airport. Larger airports handle more flights, and multiple runways allow traffic to be split between passenger planes and cargo. In AWS, network scaling ensures traffic flows smoothly even as demands increase. AWS's Graviton processors deserve special attention. These ARM-based chips deliver excellent price-to-performance ratios and consume less power, reducing both cost and environmental footprint. Many modern workloads run seamlessly on Graviton, making it a preferred option when compatibility is not an issue. Beginners should think of Graviton as the hybrid engine in a car. It gets you farther on less fuel while performing as well or better than traditional engines. For exam scenarios that mention cost efficiency or sustainability, Graviton is often the implied answer. Licensing is a subtle but important factor. Some commercial software is licensed per CPU core. Choosing an instance with more cores than needed can inflate licensing costs unnecessarily. Beginners should see this as paying for theater tickets. Buying extra seats for people who never show up is wasted money. Right-sizing instances based not only on performance, but also on licensing terms, avoids overspending. On the exam, licensing often appears conceptually, reminding you that core counts influence more than just compute. Application compatibility also matters. Amazon Machine Images, or AMIs, and drivers may behave differently across instance families, especially when switching between x8664 and ARM architectures. Ensuring software stacks support the chosen family is critical before committing to migrations. Beginners should think of this as making sure the tires you buy actually fit your car's rims. Without compatibility, even the best-priced instance won't serve your workload effectively. Testing and validation prevent costly missteps. Speaking of testing, methodology is crucial. The best practice is to run representative workloads, monitor metrics with CloudWatch, and compare across instance types. Synthetic benchmarks may not reveal real-world behavior. Beginners should imagine test-driving cars on the actual roads you'll use rather than only on a closed track. CloudWatch provides evidence about CPU, memory, storage, and network utilization, helping you validate right-sizing decisions. Iteration leads to confidence and efficiency. Costs can be tricky because instance sizes don't scale linearly. Doubling the size may more than double the price, and idle capacity becomes waste if workloads don't use it. Beginners should picture buffet dining. Paying for unlimited food is wasteful if you only eat a little. Choosing smaller, well-matched instances often saves more than scaling up prematurely. AWS encourages cost awareness, and the exam expects you to recognize that idle waste is a real risk. Resiliency should never depend on a single instance type or size. High availability comes from running auto-scaling groups across multiple availability zones, not from assuming one large instance will never fail. Beginners should see this as running a bus fleet rather than depending on a single giant bus. If one fails, others continue to operate. Exam questions often emphasize this point. Resiliency is about distribution, not reliance on one oversized resource. From an exam lens, you'll often be asked to select the instance family that aligns with a workload description. If the task involves a memory-intensive database, the answer is a memory-optimized family. If it's heavy number crunching, compute-optimized is correct. If it's balanced or unpredictable, general purpose is best. Storage-heavy workloads point to storage-optimized families. The key is to listen for cues in the question: large dataset in RAM, high IOPS or CPU intensive, and map them to the right family. Common pitfalls include over-provisioning memory or CPU, leaving resources idle. Developers sometimes choose larger instances than necessary just to be safe, but this wastes cost without improving performance. Beginners should remember that AWS makes scaling up easy. It's often smarter to start smaller, monitor with CloudWatch, and adjust upward if needed. This iterative approach avoids overspending and keeps environments aligned with real demand. Finally, documenting standards for instance use ensures consistency across organizations. Many companies maintain approved instance lists by workload type, guiding developers to the right choices. This prevents shadow IT and ensures workloads align with governance, security, and cost policies. Beginners should think of this as a company handbook that outlines which tools are approved for which jobs. Standards reduce guesswork, enforce best practices, and create a shared understanding of resource selection across teams. In conclusion, EC2 instance families provide flexibility for every workload profile, from balanced web apps to memory-intensive databases and storage-heavy analytics. The key is to match the resource profile to the right family, validate with testing, and adjust iteratively. For learners, the lesson is that instance choice is not one and done but an ongoing process of observation and refinement. By measuring, right-sizing, and documenting standards, you ensure AWS compute environments remain efficient, resilient, and aligned with business goals. That concludes today's episode of the AWS Certified Cloud Practitioner Prepcast. Be sure to tune in for the next episode and visit us online at baremetalcyber.com or cyberauthor.me for more resources, including news, mailing lists, YouTube videos, podcasts, and much more.